Okay, Assalamualaikum warahmatullahi wabarakatuh. Greeting everyone. My name is Shakyla from Class Fluid Mechanics 03. So in this video, I want to share and present my tags about final exams. Okay, first we're gonna discuss for number one. The question is an air flow up to 10 of standard is expected. 0.25 diameter that an orifice meter is used to measure the rate of flow. The manometer available to make the measurement has a maximum of 300 millimeter of water. Determine the diameter of the orifice place that should be used with D and D per 2 pressure taps. Determine the head loss if the flow area at the vena contracta is 0.65 of the orifice diameter. So as usual, we gonna solve this question or this problem using the E5, which is the first step we need to use is intention. This in here, my intention or the first step that I need to remind is trying to solve this equation. Of course, finish this problem, we have to conscious and involve our gut in every step that we pick. From the equation, number one, there's gear. Okay, that need us to find out more about airflow rate. My intention to determine the diameter of the orifice place and determine the head loss because I want to make my to know more my gut is Allah Subhanahu wa Ta'ala. Okay, so in this question is we need to determine the diameter of the orifice plate to measure the air flow rate of 1 meter cubic per second in 0.25 meter diameter touch. Using an orifice meter, the orifice meter employs D and D per 2 pressure taps, and the measurement is constrained by manometer with a maximum range of 300 millimeters of water. We need to calculating the head loss in the flow area at vena contracta. The narrowest point downstream of the orifice is 0.65 of the orifice diameter. Okay, so after uh, we the first step is intention. We need to move to the second step, that is initial thinking about the problems. So in here, I make an illustrate from the question. So this is the illustrate. So first thing first, we need to gather all of the data that known from the question. So in here, from the question before, we know that orifice diameter airflow is 1 meter cubic per second. And pressure difference is 300 millimeters water. And the head loss of the orifice water. So we in here, in this step, we make an assumption that is the airflow is steady and it can be treated as an incompressible flow. Good. So we move to the next step, which is idealization. So in idealization, we gonna put a lot of formula to solve the question. So here we got a formula that is mass is equal to C times A root differentiation of height per B power of 4. And from the equation we have now that C is the coefficient of orifice. And then is the differentiation have the formula that are P1 minus P2, and then B is the diameter. So from the P1 minus P2, we have the formula also, that is P1 min P2 is equal to 1 min before for 2P, 2 rho. So yeah, we got the equation from here. So P is rho is the form we know is standard of air density, that is 1.23 kilogram per meter cubic. So from the mass equation that we have, we need to find the Reynolds number. That is formula is, we can see the formula in here. Okay, so in the day when we exam, actually I finished the step only from the intention to the idealization. So in here, this video, I'm gonna continue the step that is instruction. So in the instruction, we need to, oh, okay, sorry, this is actually, there is a continue the initial thinking about the idealization. So we have the Reynolds number formulas in here. So after that we can also, there is a height equation is P1 min minus P2 per row. So the equal to P1 min P2 times row 3 min P3 min minus P2 per row. So after that we can move to the next step, that is instruction. In here we can put some data into the formulas that we gather from the Reynolds number. We get the equation and we can put the numbers in here. And from the equation and numbers, we get the Reynolds number is 3.50 times 10 power of 5. And then the P1 minus P2, we got also a number that is 2070 Pascal. Okay, after we got the differentiation of pressure, in here we can also find the pressure from P3 minus P2 is actually, we got this number is 1490. After that, we can also find the height is from the formula that we have got in idealization, and we got number is 1250 Newton meter per kilogram. So for the final question is, we need to evaluate the permanent head loss. The question, the result is, we from here we got a formula that is P1 minus P3 for P1 minus P2, and we got from the before formula we got 1250 per 2830. We got the number, the head loss is 0.44. Okay, so this is for the number 2, spray heads in agricultural spraying system to be supplied with water through 500 feet of a draw aluminum tubbing from air engine driven dump. Okay, so it is in its most efficient operating range. The pump output is 1,500 GPM at the discharge pressure, not exceeding for 65 C. For satisfactory operation, the sprinkle must operate at 30 C or higher pressure. Minor losses and elevation changes may be neglected. Determine the smallest standard pipe size that can be used. Okay, so of course, first we need to determine this intention. So from I read the equation, I realized to finish this question, and we need to stress first. My first intention for this question is I want to understand and accelerate this equation because of my God, and I want to determine the smallest standard pipe size that can be used in agricultural spraying system. So in here, we need to calculate the head loss. Is the given flow rate is 1,500 GPM and the length of the pipe is 500 feet. To calculate the head loss due to friction of in the pipe, uh, it, this involves using a Darcy-Weisbach equation or the Hazen-Williams equation, commonly used for water flow in pipes. So we need to select the pipe size. We need to identify the smallest standard pipe size that with that will result in a pressure drop such that pressure at the sprinkles remains at or above 30 C, and taking into account that the maximum discharge pressure from the pump is 65 C. Okay, after we have determined the patient, we move to the next step, that is initial thinking about the problem. So in here, okay, so this is the visualization or the modeling that from the question. We got a pump that is a length for 500 feet, and also the Q is 1,000 and 500 grams. Okay, first thing first, we need to found the maximum allowable pressure drop over the length. So is the equation is delta P max equal to P1 max minus P2 max, P2 min is equal to 65 minus 30 C. That we can get is 35 C. After that, we can use a governing equation. The Bernoulli is actually, we can see the equation in here. We can to eliminate the equation in here, that is the location in the x, the okay, so we can eliminate few component in here, and we got is from the first place to the final place, we can minimize, and the equal is 0. Also in this uh, initial thinking, we need to have an assumption, and we need to determine the assumption. That is, the first one is steady flow, second is incompressible flow, and then question 1 is equal to equation 2. Okay, so this is the illustration, which is we need to gather all of data that we need. We need to determine and gather all of the formulas that we need to know. So, of course, we have in here we have a Reynolds equation. Of course, the value Q is 1,050 kilogram, and we need to change into feet. And to be Q is equal to 3.34 feet cubic per second. Next. Okay, so we need to move to the next step, that is instruction. We got the Reynolds number is equal to 6.95 times 10 power of minus 5. Also, we need to find the delta P. This is the equation, and we got number is 240.24 each. So after that, we got the Reynolds number and delta P. We need to move to another instruction. We need to in here, and we need to assumption that the diameter is 5 inch and the P is 1.2 times 10 power of minus 5, and the this number of pipe is equal to 0.0122. Now we get the final result. The criterion of the pressure drop is satisfied for minimum maximal diameter of 6 inch is 56.4 pound per inch square. Okay, next we move to question number 3. In here, we also have a question in here, a tractor. Weighing is 1,600 pound, attains a speed of 270 mph in the quarter mile. Immediately after pressing through the timing lights, the driver opens the drag circuit of area. A is equal to 25 feet. Air and rolling resistance of the car may be neglected. Find the time required for the machine to decelerate to 100 mph in standard air. Okay, so we have first thing first, as usual, the intention from the question that we got, the make consciousness. I have the intention that I want to find the time required for the machine to decelerate to 100 mph in standard air. Also, I want to finish this problem intended to know Allah subhanahu wa ta'ala more. Okay. So in here we can see the given data is just dragster weighting is 1,060 pounds. Moving with initial speed is 270 mph, slow by drag force, and sheet of area is A is equal to 25 feet, and negative air and rolling resistance of the car. Okay, so in here we can see the air is standard. We can make an assumption that is standard air. Okay, so first thing first, after we found, after we determined the intention, we move to initial thinking about the problem. So this is the how I illustrate the question in here. We taking the car system and writing Newton's second law in direction of motion gift. So there's force, there's speed, the position, and we know the weight is 1,600 pound. Now, okay, so after that, we move to the next. Okay, so this is the idealization, which is we need to gather all of the formula that we need to use in this question. Okay, first question is F is equal to MA times N delta dP per dt. That's for the first equation. Since C is F per so we have the equation for the C. We can substitute the F0 to the fourth formula, and it can be substitution equation 1 and the equation 2, and we got the final equation 1 per 2 C rho phi square times A is equal to m dot dp per dot dt. Okay, so after we can use this pattern variable, we need to integrating the formula, and we got the result of the integrate is integrating from p0 to p1 dv per v square. So after that, we need to know about time. So we get the formula that is t is equal to p0 minus p final per p0. So we got the equation is 2 omega per c rho a g. Okay. Okay, also for the question number 2, we need to know about the Reynolds number also. There is we got the Reynolds number is actually from usual equation. And then we can process all the formula force, Newton's second law, and now we need to put the number into equation time that we have obtained. That is, the times is equal to 5.05 seconds. Okay, next, this is the fourth question. We got to flow in open channel. For number 1, first thing first, of course, we need to know our intention is from the question and the picture that we get. I have a conscious to find the value of c and the rate speed. Okay, so for the one is valid for the control volume in shift coordinates. For number 2 is obviously valid for our liquid flows. And the assumption 3 and 4 are commonly used for all the channel flow. And assumption number 5 is valid in this case because we assume the area of which is B delta x is relative to the small of the total friction force is negligible. Okay, next. After that, we need to initial thinking about the problem. Mentioned in the question, there are fluid moving at speed is equal to c times t0. Is obtain the value of the speed, we need to consider an open channel move. So there is some question for incompressible flow with the uniform velocity at each section. The continuity equation is sigma cs v or speed times a for the area is equal to 0. After we know the idealization is actually in this video I want to put idealization more. So in here we got the c minus delta v is times with y plus delta y times b mean cyb is equal to 0. So the surface force consists of pressure. Um, Force the two ends by assumption. We neglect friction. The gauge pressure at the two ends in hydrostatic as illustrated from that we have met. And the hydrostatic is force Fr on a submerged vertical surface of the area, or A, is given by the simple result. Okay, so we need to differentiate the formula. We need to check it out the formula and then we get the instruction. The instruction that we get is the two terms in range are equal from continuity is shown like this equation. So the moment we need quantum momentum equation to know to answer this problem. So the equation is g y delta y plus g delta y squared per 2 is equal to y c dot delta p. So in here we got the final c that is equal to root g times y. Okay, so this is the question for number 5. the air flows isentropically through a converging nozzle at a section where the nozzle area is 0.013 feet. The local pressure, temperature, and the Mach number are 60 C, 400 Fahrenheit, and 0.32 respectively. The bag pressure is 30 C, and the Mach number at the throat, the mass flow rate, and the throat area are to be determined. Okay, so first, of course, we need to know the intention. In this question, we have a converging nozzle, and there are the airflow through the area. And my intention is I want to determine the Mach number at the throat, the mass flow rate, and the throat area because genuinely because Allah subhanahu wa ta'ala. Okay, next. We move to the initial thing about the problem. From the question that we have, we can gather all of the data. That is mass is M1 is equal to 0.52. For the temperature is T1 equal to 440 degrees Fahrenheit. For the Mach number is equal to 60 C, and the nozzle area is equal to 0.013 feet square. Okay, first, after that, we need to move to the idealization. So first, we check for checking is we need to determine if flow is isentropic down to P. To check, we evaluate the stagnation conditions. So we have a formula. A formula is pressure, initial pressure is equal to pressure 1 times 1 plus K minus 1 per 2 equal to mass power of K per K minus 1 is equal to 60 C. Okay, so next, after we have determined the flow isentropic down, we need to know the back pressure ratio. The formula is rho B, PB per PO per 0. Also, we need to know the TS diagram, the mass flow rate, and may be found using PVA. So from there, we have a question. V1 is equal to M1 times C1 is equal to M1 root KRT. So after that, we got the number of V. We can substitute into the equation, which is A1 per A, A is equal to 1 per M1 is, and time the equation from here. So after the final equation that we got, we can move to the instruction. The instruction from the question, we just only need the question, the formula that we have gathered all of them, and we have a final equation in here. After that, we need to put the number into the equation. So we got the number of the result of AT, or the last area, is equal to 9.98 times 10 to the power of -3 feet square. Okay. So in here we can see that the shock flow is actually AT is equal to 8. Okay, next. Okay, so that is all from me. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.